What do you see for Starlink being used as a relay, let's say around the moon, or for comm relay all the way to Mars and back?
Mars, you'd want basically like a laser relay system. Essentially, it sort of depends on what bandwidth you're looking for. Obviously, in order to have continuous coverage with Mars, you'd have to have some relay system because you can't transmit through the sun. So when Mars is on, when the sun's between you and Mars, you have to do a bank shot through a relay satellite so that your photons don't have to go through the sun. Ultimately, we would want terabit, maybe petabit level data transfer between Earth and Mars. You're gonna want probably some relay satellites along the way to be able to do that. It's a bandwidth thing. You'd want to use lasers, and then the laser beam is going to widen with distance, so that then you need to be able to receive the laser beam before it gets too wide. This means that you need a series of satellites in order to communicate with Mars at its furthest distance, especially with very high bandwidth. You can obviously do low bandwidth with longer wavelength photons, but if there's a human city on Mars, you'd want to have very high bandwidth. So therefore, a bunch of lasers.
Hey, this is Warren Redlich. As SpaceX prepares to take humanity to Mars, the journey to Mars will involve specific problems that people aren't talking about very much, and that particular problem is communications. We all know about the latency problem, that time it takes to travel, once the Starship gets on its way to Mars or from Mars, the time it takes for a signal to travel to and from Mars, to Earth from Mars and back, is very, very long. But something we don't talk a lot about is bandwidth. How will the signal travel? How big of a signal will people be able to send back and forth from Mars to Earth, and from Earth to Mars, and from starships or other spacecraft to and from Mars or Earth as they're traveling? As humans land on Mars and begin to establish a presence, the ability to communicate from Mars to Earth and from Earth to Mars and back, and to be able to communicate a significant message, will matter a whole lot. So let's talk about a way we can do that better. I propose an idea that will help with that bandwidth problem. A network of Starlink-like satellites orbiting the sun to relay signals between planets, allowing a much greater bandwidth and improving communication for Earth, Mars, and spacecraft traveling between them. Earth and Mars are far from each other. Distance varies from roughly 35 million miles or 55 million kilometers out to 250 million miles or 400 million kilometers, with an average distance of about 140 million miles or 225 million kilometers. Any signal sent from Earth to Mars or from Mars to Earth will take an average of over 12 minutes to arrive. Round-trip communications will take nearly 30 minutes. Here on Earth, most modern communications have a latency of much less than 1 second. It's about 1.3 seconds each way to the moon. So the jump to Mars is huge. Our communications with a Mars colony will still be much faster than long-distance communication was before the telegraph, but the delays will be uncomfortable to everyone alive today. A solar-orbiting Starlink network will not solve this latency problem. It will actually increase the delay slightly because the signal will travel around the network instead of on a straight line. Also, each relay will add a very small delay. With the current presence of humanity on Mars in the form of the Mars rover, the rover on the surface communicates with orbiters which send and receive signals to Earth-based antennas. Signals are transmitted in a straight line, but bandwidth is low, no more than 4 megabits per second. This is an extremely narrow pipe for the purposes of a colony. The current method is also limited by Mars rotation obscuring the rover from orbiters and/or orbiters from Earth, as well as the brief moments when the sun is between Earth and Mars. A Mars ground-based antenna system similar to the one on Earth would help, but it would take a huge effort to build it on Mars or deliver it to Mars, and would require a huge amount of power that is not easily available. NASA has been working on laser systems for communication and anticipate that this would increase bandwidth. Elon tweeted that high-frequency lasers would be the way to go. This sounds good, but it's still a challenge to deliver sufficient bandwidth over the very long distance from Earth to Mars. Even at 100x the current 4 megabits per second, 400 megabits per second is still a very small pipe for 1 million people. It's small even for hundreds of people. It's barely faster than what a common home internet connection has today. The plan I propose later in the video does use lasers, just as Starlink satellites use lasers in Earth orbit. I've heard some talk about using satellites positioned in Lagrange points for Earth, Mars, and/or Venus. Lagrange points are somewhat stable spots where a satellite can orbit the sun while maintaining a relatively constant position in relation to the planet it is near. This still seems a challenge. The satellites would need a lot of power, which might be harder to provide in space. The L4 and L5 Lagrange points are a substantial distance from the planets. The L2 Lagrange point for Earth and the L1 Lagrange point for Mars are not truly stable, so maintaining position can be another challenge. Bandwidth is affected by the inverse square law. When something is broadcast at a distance twice as far, you need 4 times as much power, or if you use the same power, the signal received is only 1/4 the strength.
How well spray paint coats a surface depends upon the distance. Up close, the paint quickly coats. Farther out, the spray is spread out, less concentrated. Double the distance, and you have 4 times the area to coat. Tripling the distance gives you 9 times the area. Quadruple the distance, and it's 16 times. Way out here, it'll take a long time for a unit square to get fully coated.
So the big idea is to use a network of satellites to relay the signals from one planet to the other. With Mars and Earth being anywhere from 35 million to 250 million miles apart, it's very difficult to carry a lot of bandwidth, but a network of satellites relaying signals greatly shortens the distance of each step, and that should allow for greater bandwidth. Consider the simple example of a single circle or oval of satellites about halfway between the Earth and Mars orbits, roughly 20 to 25 million miles from each. Earth's orbital circumference is about 600 million miles or 940 million kilometers. Mars' orbital circumference is 870 million miles or 1.4 billion kilometers. So figure this single loop of satellites would have a circumference of roughly 720 million miles or 1.2 billion kilometers. If each satellite is 20 million miles apart, that works out to 36 satellites. A signal from Earth would travel roughly 20 million miles to the first satellite, and the relays would each be steps about 20 million miles as well. Thanks to the inverse square law, when the Earth and Mars are close together, 40 million miles or so apart, that reducing the hop from 40 million miles to 20 million miles, having the distance quadruples the bandwidth. They get 4x. It's when they're further apart that it really shines. So the average distance between the Earth and Mars is 140 million miles. So shortening that 140 million mile distance to 20 million mile hops is a 7x improvement, but in terms of bandwidth, it's a 49x improvement. And when you go out to the maximum distance of 250 million miles, that improvement ends up being 150x. You get 150 times the bandwidth when the Earth and Mars are at their farthest with this single, simple loop network of only 36 satellites. There are some key distinctions between Starlink covering the Earth and comparable satellites in a network around the Sun to facilitate Earth-Mars communication. Starlink circles the Earth as a globe. It has to cover nearly all of the planet's surface, so the satellites occupy multiple planes and travel at different angles. It's a complex pattern that requires over 10,000 satellites and maybe over 40,000. Each satellite has to handle numerous connections on the ground and at the same time maintain contact with other satellites via lasers, something that could be useful for the solar orbital network I have in mind. The Starlink Earth network involves fairly short distances. Each satellite uses a phased array radar antenna to communicate with the fairly simple antenna we'll use on the ground. That's usually less than 500 miles in distance. The satellites also use lasers to communicate with each other. Again, these laser connections would connect at distances in the hundreds of miles. It is thought that each satellite would connect with perhaps 4 other satellites, and the network would relay signals from one place on the globe to another through these relays. So now let's picture the same idea used to communicate between Earth and Mars. The satellites don't have to completely encircle the sun the way that the Starlink satellites have to encircle the Earth. They only need to be in a flat plane. Earth and Mars have nearly the same tilt to their orbits, 24 degrees roughly. So the Starlink satellites between Earth and Mars could operate in that same rough plane at about 24 degrees orbiting the sun. By simplifying to the 2 planets and the satellites orbiting in one flat plane, That greatly reduces the number of satellites we need. A big concern is making sure the satellites have enough power to transmit over the distance, and 20 million miles is still a long haul. If we can shorten the distance between satellites, we can reduce the power that they need to communicate or increase the bandwidth that they can send over what power they do have. We can do that by increasing the number of orbital loops, the steps between Earth's orbit and Mars' orbit, and increasing the number of satellites in each orbit. By doing this, we can reduce the distance between the relays and increase the bandwidth even more. So let's see what happens when we cut the 20 million mile distance down to a 5 million mile distance. Let's look at those numbers. By my calculations, that's 9 orbital loops, starting at a 97 mile radius, 97 miles from the sun, 5 miles further than the Earth is, expanding by 5 million miles at a pop, starting at 102 miles, 107 miles, and so on, out to 138 million miles, which is 5 million miles short of the Mars orbital radius. Satellites in each loop are separated from each other by 5 million miles. The smallest loop has 122 satellites for the circumference of that loop. The largest loop has 173 satellites, for a total of just over 1,300 satellites. Since a single Starship is expected to be able to launch 400 Starlinks in one go, the entire network could be deployed with just 4 launches, although the farther orbits might require some refueling in low Earth orbit. Now, each step between relays is only 5 million miles in distance. Still actually very far, but 5 million miles is a lot less than the 40 million miles or so when Earth and Mars are at their closest. That's 1/8 of the distance, which means 64 times the bandwidth, or 1/64 of the power needed. At the 140 million mile average distance between Earth and Mars, the same power level of signal can carry nearly 800 times the bandwidth. At the long distance of 250 million miles, it's 2,500 times the bandwidth. That's a monster difference. The system has several other advantages. Bandwidth is consistent regardless of how far Earth and Mars are apart. Additional satellites increase network reliability. Multiple paths allow a further increase in bandwidth. 9 orbital loops means potentially 9 additional paths to travel, or 9 times more bandwidth. On top of that, if there's no hurry, you can also send traffic the other way around the sun, the long way, and that's an additional 9 paths, or another doubling of the bandwidth that you would have compared to that first 9. The sun is never in the way. That's not a huge problem most of the time, but it's about a week every 2 years or so that the sun gets in the way and makes planet-to-planet transmission very, very difficult or impossible. This solves that problem. A huge bonus is for spacecraft traveling between Earth and Mars. They have limited resources, and requiring them to manage the power to be able to transmit back and forth to Earth or back and forth to Mars is an additional burden on the spacecraft for the journey. By using this solution, there will always be a satellite in an orbit within about 5 million miles, so it will be much easier to communicate either back to Earth or to Mars, or to other spacecraft traveling in the area. We can take this a step further and go to 2 million miles apart. Now the orbital radius starts at 95 million miles and goes out in 2 million mile steps in 24 loops to 141 million mile radius just inside the Mars orbital radius. The smallest loop has 299 satellites, and the largest has 443. That's a total of nearly 9,000 Starlink satellites, and it would require maybe 25 Starship missions to get this done. The 2 million mile relay distance means 400 times the bandwidth when the planets are close, and over 15,000 times the bandwidth when they're at their farthest. Having that 24 loops also increases the bandwidth 20x, because you've got 24 different paths to follow, not to mention you can go back around the other way. The network could optimize traffic. The traffic that needs the most speed could take the shortest path. Traffic that doesn't need the highest speed can take medium length paths, and traffic that doesn't require any particular latency could go the long way around the sun. Also, satellites that aren't being used by the network could be used for other purposes. Maybe it would be possible to add some kind of instruments or optics for these satellites to be used for astronomy, for example, to look for planet-killing asteroids, to look for other things in the sky, to listen as a part of the search for extraterrestrial intelligence, to do wide-angle aperture astronomy. Even with all I've said, this network might still be insufficient. As the colony grows to 1 million people or more, you could take the system a step further and go to 1 million mile distances or even closer, increasing the number of satellites. A 1 million mile network would have 49 orbital loops and a total of over 36,000 satellites. Shrinking that relay distance by half would again 4x the bandwidth. And then adding the extra loops would again increase the bandwidth. So that's the big idea. There's a little bit more to talk about though. In my conversations, some people suggested the orbital loops could actually go inside Earth's orbit towards Venus and Mercury. When Earth and Mars are far from each other near opposite sides of the Sun, it would further shorten the distance that the relays would travel, and it would add additional paths that would increase the bandwidth. It would cost less to put satellites into those orbits because there would need to be fewer of them. Going beyond Mars, out towards Jupiter and out to the asteroid belt would be much more challenging. The distances become much greater, the circumference of the loops becomes much greater, and so the cost of adding additional loops outside of Mars' orbit would start to get very, very expensive and difficult. It's not impossible, and if there's a commitment to make it happen, it's doable. It would just be a lot harder. How about cost? The current Starlink satellites that are being used for the Earth network cost in the ballpark of $250,000 each to build. It may very well be less expensive. SpaceX may be finding ways to save money on that. The solar network satellites, the ones that are used for communication between Earth and Mars, would be simpler in some ways. The Earth-based Starlink satellites have to have phased array radars to communicate with people on the ground and satellites on the ground. The solar network satellites don't need that hardware. It's just the lasers. Now, the lasers would need to be more powerful, because they have to cover much longer distances, so that kind of offsets each other. So as a ballpark figure, these satellites should cost about the same as the Starlink satellites cost now. Could be more, could be less, but about the same. The solar network also doesn't need to spread its bandwidth over so many different users. They're going to be communicating with 1 to 4 satellites at a time, rather than communicating with hundreds or thousands of people on the ground. So that allows them to channel all the bandwidth they have available into a very small number of signals. Between launch cost and satellite cost, it should be possible to deploy the 2 million mile network for the same cost as deploying the Starlink network around Earth, maybe less. To clear up one thing I could see people asking about, with Earth-based satellites, we worry about the Kessler syndrome, that there's too many satellites up there, something collides with something else, and it creates a huge amount of debris, and it makes it difficult to use orbit or difficult to get things up into space. This is less of a problem than people think it is in Earth orbit. It's a problem, but it's not that big of a problem. It is far less of a problem when we talk about orbiting the sun. Space is really big. Really, really, really big. For starters, we're just talking about one plane of an orbit around the sun, when there's so many other levels that debris, satellites, spacecraft could occupy. Even if you work just within that plane, and you figure the 1 million mile version of this network, and let's say you have 36,000 satellites in that network, and each satellite is 1 million miles apart. If each Starlink satellite is 10 feet long, which is about right, that's 1/500th of a mile. That makes the chance of a spacecraft or some other object hitting one of these satellites 1 in 500 million, assuming they're in the same plane. But they're not all in the same plane. There's a lot of room vertically as well. And the Starlink satellites are not very tall either. So we're looking at probabilities that are so small, we can't really even comprehend them. Can you think of a better way of doing this? Do you think it's unnecessary and that stationary lasers will be sufficient? I don't, but I'd like to hear what you think.